In this video, we are going to be solving a kind of tricky oscillatory motion problem involving energy. It's tricky because it's more in the style of an AP exam, so some of it seems to be a little less straightforward. So, the potential energy of a simple harmonic oscillator is given by U equals kx squared over 2, when x equals 0 is the relaxed equilibrium position. The spring constant K equals 10 newtons per meter. Part A, if xt equals a cosine omega t, where a equals 0.25 meters and omega equals 2 pi, plot the potential energy versus time for 3 full periods of motion. B, explain why the period of the potential energy is different than the period of the position function. Calculate the value of the mass of the oscillating object. Write the expression for the kinetic energy using the fact that omega t plus kt is constant and the fact that cosine squared plus sine squared is equal to 1. And then we also want to add that kinetic energy function onto our plot. So there's kind of a lot going on here. So let's just take it step by step. So the position function is equal to a cosine omega t. And we want to take that position function and see if we can somehow get it into an energy function, because what we want is this right now is our energy function, and we've got energy as a function of position, but what we want is potential energy as a function of time. So we somehow have to take this and turn it into a potential energy function of time. So what I would do is I would start by rewriting that as an actual function. So xt is equal to 0.25 times the cosine of 2 pi t. And it says we want to plot it for 3 full periods of motion. So I think it would be a good idea to figure out what a period of this function is equal to. So remember that this right here is omega. Omega is equal to 2 pi. And we know that t is equal to 2 pi over omega. And that's just from our standard formula sheet. So if we plug in 2 pi for omega, we get that 1 period is equal to 1 second. So 3 periods would be equal to 3 seconds. So on the x-axis, we want to go out to 3 seconds. So this is our position as a function of time, and this is our, again, it's our energy as a function of position. So what if we just wrote that out? And what if we took this and plugged that in right there? So first, and we also know that k is equal to 10. So I'm going to take this 10 and plug it in for k. And I'm going to take this whole function here and plug it in for x in that equation. So this is our energy as a function of time, but we should definitely simplify it so that it is easier to plot. So first, I know that 10 divided by 2 is 5. And then I want to simplify this part by distributing the squared to both the 0.25 and the whole cosine function. So 0.25 squared is 0.0625. And then the whole cosine function will be squared. And we can just continue simplifying that. So I just want to distribute or, multiply that whole thing by 5. And this is my energy as a function of time, this expression right here. This makes sense because this right here is what the maximum potential energy will be. So that corresponds to this amplitude here in the position function. Perfect. Let's go ahead and plot this. What I think would be a good idea before you plot it is you can just plug this into your graphing calculator. And I plotted it on Desmos. So this red is my position function. So I can see clearly that 3 seconds corresponds to 3 full oscillations. And then I can also see that the period of the energy function is half the period of the position function. So basically, I've got twice as many bumps up here above the x-axis than I do for the position function. So we'll talk a little bit more about that later, but notice that since this cosine is squared, then that's going to mean that the energy function is never negative. So that's why for the blue, the energy function, there's nothing below the x-axis. So I basically just modeled my graph after what I graphed on my graphing calculator. I thought it was a little bit clearer on Desmos. So I'm going to go out, that's 1 second. And then maybe I'll go back and look to make sure I'm doing it right. It should look something like that. And part B asks, explain why the period of the potential energy is different than the period of the position function. What I had said earlier is that the period of the energy function is half that of the position function. So let's go back to my graphs. So again, it takes 1 second for the position function to get back to its original position, but it only takes half a second for the energy function to get back to where it originally was. So let's think about why that's the case. Well, the amplitude of the position function is 0.25. So every second, it gets back to positive 0.25. Every half a second, it gets to the absolute value of 0.25. So at 0 seconds, it's at 0.25, and at half a second, it is at negative 0.25. Remember, in the potential energy function, elastic potential energy is equal to 1/2 kx squared. So when you square a negative, it's the same as when you square the positive of that number. So basically, the potential energy is going to be at its maximum twice as often as the position function will be at its maximum. So hopefully that makes a little bit of sense. Okay, then for part C, we want to calculate the value of the mass of the oscillating object. So we should have gotten quite a bit of practice with this by now. So remember that omega is equal to 2 pi, and we know that the period of a spring is equal to 2 pi times the square root, and this is part C, of m over k. And then also from our formula sheet, we know that the period in general is equal to 2 pi over omega. So what I'm going to do is I'm going to solve this whole thing for omega, and then I should be able to solve it for m, because remember, I'm trying to get m for part C. So I'm going to cancel out those 2 pi's. So then what I'll end up with is the square root of m over k is equal to 1 over omega. And then I will multiply both sides by omega. Then I'll square both sides. And then I will solve this expression here for m. So if I solve that for m, so I'll get omega squared m, multiply both sides by k. and then divide both sides by omega squared. So m equals k over omega squared. And it gives me my k. My k is 10 newtons per meter. And then my omega is that 2 pi. And remember when you type that into your calculator, make sure you have parentheses around the 2 and the pi. And you should get that the mass is equal to 2.53 kilograms. Okay, the last part of this problem is we want to come up with an expression for the kinetic energy rather than the potential energy. So we're given the information that cosine squared theta plus sine squared theta is equal to 1. Okay, so we know that in oscillations, mechanical energy is conserved. And we know that the maximum potential energy that the object has is equal to, I'm going to write U max, is equal to 1/2 kx squared, where x is the amplitude. And so I'm just going to plug in A for x, A standing for the amplitude. So I know that at any point, the kinetic energy at that point plus the potential energy at that point is going to equal this right here. So the kinetic energy is going to equal the maximum energy that the system can have minus the potential energy at that time. So let's find 1/2 Ka squared. And it's 0.3125, which makes sense because that's the maximum the potential energy can be. That's like what was on the outside of the cosine squared in our potential energy function. So now what I'm going to do is right here, I'm going to plug in that potential energy function we came up with earlier. And now I'm seeing that in each of these terms, I have a 0.3125. So I'm going to factor that out. And look, this is the part where I can use cosine squared plus sine squared is equal to 1. If I solve that for sine squared theta, I get that sine squared theta is equal to 1 minus cosine squared theta. So, and look, I have a 1 minus cosine squared term in there. So it's going to be equal to 0.3125 times the sine of sine squared of 2 pi t. So that is my kinetic energy function. Now I want to add that kinetic energy function onto my graph from earlier. And remember we talked about before that sine and cosine are 90 degrees out of phase with each other. And we also talked about how kinetic energy and potential energy are opposites from each other in terms of when they are at a maximum and when they're at 0. So the sine function starts out at 0. So whenever the potential energy function is at 0, the kinetic energy function will be at a maximum, and vice versa. And that's adding the kinetic energy function along with the potential energy function. So this problem was a little bit complicated, but we just used what we knew to figure it out. And it makes sense in terms of the concepts that we've learned.